Hello, hello. I'm back again. Another cup of tea. Second session of the day. I'm quite happy that we managed to get some assembly going in the last session, even though all it was an exit. I feel like we spent way too much time basically just trying to figure out how to write a file in Odin. Um, I guess there's going to be some things like that. It's a new language for me, so there's always going to be um, these kind of issues where it's something I haven't done in the language yet that I need to figure out. I mean, the actual meat of the code I feel is not very complicated so far, especially on the compiler side. You know, we've taken the tokenizer is the most complicated part. You know, that's some complex, reasonably complex code. Let's stretch this across here so we get a bit more space. I mean, the main is just, the compile is just setting up our string builder, writing a little bit of entry point, and then for different things, we're going to write different assembly code. It's not rocket science. Um, Fairly simple. It's just getting this, and then it's just writing the file, figuring out how to do the string handling and writing the file is what took us so long. So first things first, I just realized, let's not worry about getting null right now. But we'll just go 05 compiler with halt is what we got. Actually, that was part of 04, wasn't it? Episode 4, you could say. I did two commits for that one. Okay, so we're all up to date. We output this assembly where we have an entry point, and we have two halts because we compiled this program, which includes two halts, and halt was the only thing that we're handling so far. I think I did put the exit code back to 0. So if we run that again, we'll find that it's putting 0 in RDI. All right. So far, so good. So now I feel like because we've gotten past all the string handling bullshit, we can get into some more interesting stuff. In this episode, I guess you could say, in this video, what is it that we want to attack? Well, I think we want to try and get this program running. If we could get this program running in an hour, I think that would be amazing. I think the first thing to try is this print, because I think that can run in isolation. A jump, maybe jump is we can't have a jump without having something to evaluate. So maybe we can print, then we can read. We can do a read operation, and then we can just jump based on the read. And then we can get into the sub, do two reads and a sub, and then do the jump. And that's basically it, actually. That's the whole program. Okay, that's what we'll do. So print. I think in order to print, what we want to do is go back to our, don't need this stuff anymore. Let's just go back to Odin docs homepage. It's nice to have. But here we have our syscalls. This is where we figured out how to do our exit, which was down here. I'm not even sure what we're looking for. I think it's like write. I think we want to write, and FD is like the file descriptor. And I think from memory there are like some reserved file descriptors, like I think 0, 1, 2 is like maybe standard in, standard out, standard error. Let's go to the man page for write. Write file descriptor. Where's the errors, standards, histories, bugs? Where does it explain what the parameters do? I feel like that's an important thing to do. By the file descriptor fd, if count is 0, and fd refers to a regular file because it can refer to other things. Results are not specified. FD. Okay, so these are all the errors. So that didn't really help us identify. So maybe here, oh my God. I did see this done before. Let's just wing it. We also need to specify this data. So this is going to be a bit weird, but I'm going to open up this fireship assembly. What I should do, I think I should just mute it. Sorry about that. Here's 100 seconds of assembly. And let's skip forward because he does some stuff. Okay. This is awesome. So he does a print. So this is exactly what we want. We're just going to copy this. So syswrite is 1. Yeah. And then he's saying standard out is 1 for RDI. So it's file descriptor 1. And then he's got a pointer to the data and the size of the data, which he has put in the section .text. No, he hasn't. Where did he put it? Hello, Len. He must have done it somewhere, or maybe he hasn't done it yet. Anyway, let's copy this part. He's also put a bunch of comments in there. See, I like this. He's done the same as me. He's aligned them, which is also nice. Maybe something that I can try. So let's go to our print. I want to say we're doing a print. Syscall write RDI 1, which is standard out. But then we want to do a couple more moves into RSI and RDX. RSI, RDX. Do not ask me what all these register names mean because I have no idea. But now, please, fireship. Here we go. So he's got section data, section text. Okay, let's try that. I don't know if that's, I can't remember if he was using NASM. Um, the different assemblers, they have different syntaxes and different ways of describing things. So actually this is interesting because there's two different sections. For our print command, we want to print the thing beside it. A section data and a section text. So maybe, I don't know if we can do section dot text. Let's indent things a little more. And then maybe we can keep track of our strings. We call them a string constants. String constants can be good old dynamic array of strings. Just like that. And what we also want to do is, just like we did in our interpreter, we might want to extract this at some point. But let's go to our print. See, before we printed, we wanted to do this check. I think we still need to do that. Check that we have something to print, and then move to that token. That's why we were getting this unknown token, because when it came to print, it was not doing any handling, including not moving to the next token. So then when the loop came around again, it would find this token. When only because we do this within print, it would, when the loop comes around again, it would be here instead. So we've got nothing to print. So what we're going to do is we're going to go string. We're going to go string index equals the length of string constants. And then we're going to append to string constants the token at the index. Okay? Was that the right thing to do? Yes. Because length is like index plus 1. So we get that first. And now you can see in the Fireship's code, is he like names these and then refers to them further down. So what we want to do, I feel like I don't know how we can do a string concatenation. Maybe we do a quick check. Odin string concat. Is there I don't know if there's a nice way to do it without resorting to what we're going to do. So we're just going to sort of like print out, maybe I'll put it on the same line. Okay, did not like that. But I saw something about a dot plus. Oh, let's try plus. So oh, I've done it to the wrong one. So RDI, this is the one that should be that. But RSI should be let's just call it str index. Can I do that? Can I just do that? No, I think we need to do strings like, what is it, A to I or something. Str conv. Got the cat meowing in the background. Very persistent cat. Truffle? Yeah, it's all good. It's all good. Everything's fine. That's going for string to int, so it must be I to A. Yes, Truffle. Which takes in a byte buffer and string concatenation is only allowed with constant strings. Parameter. Oh, okay. And the evaluation of this is not a constant string, so I think this is not even going to work. But we do want to convert that number to a string. Okay, string constant index. What do you want from me? The buffer to store the resulting string, the integer value to be converted. Did I use this anywhere else? No. So we need a byte buffer. I think I did use this. Wait a minute. I'm sure I used something like this, like on the read. Yeah, I think this is something similar. You know, the read does it. So if we say data 256, that's so strange. Resulting the integer value to be converted. So that's what we're converting. That's like a slice of bytes. So strange. Then we get the string. I'm really not sure about this. But we can't do this because only allowed with constant strings. So we're going to have to do this the ugly way, where first we do that part, then we do this part, and then we do the end, which I'm not a fan of. I don't like how this has split everything up and made it quite ugly. Maybe at some point we'll figure out a better way. Oh, RDX. So here it's CLion, we'll call it. we like snare case. Like that. So that's our print. So if we run that, we get a print which does a write to stand it out with str0, strlen 0, and then syscall, which looks right. It's within the text section. And now what I want to do is see if I can then just, for string constant and string constants, now I want to start a new section. So maybe I'll put a slash in at the start as well, section data, I think it was. And then for each one, we want to do, what Fireship did, because he knows what he's talking about. I do not. What the fuck is this, 10? 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then maybe a terminating null. Maybe. So we need to write two things. And I can't remember what the meaning of these things is. But first we want a str. We want the index as well, because then we put the index. But it's not a number, so we have to do this weird stuff, which I'm probably getting wrong. So it's the index str. Something like that. Oh no, it did work up there, didn't it? We've already checked that that works. So str, I think he did like space, colon space db space. So colon space db space. Opening quote. And then the string itself. So the string constant. Then we want to close the quote. So we have to do this. And then it's a comma and then the size. So we probably need to do that. And then comma space, and this is string length. String constant length. Let's just say length str. It's kind of the same as this. I'm not sure what this deal is with supplying your own buffer and stuff, but I don't know. Let's just go with it. So this time it's the length of the string constant that we want to get. Do that. So now if we run that, get our text section, global start, we have these prints, which are going to print str0, strlen 0, and we have str0, db not equal, and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, should be 12. So I think it needs to include the quote marks. If we do need to include the quote marks, I guess so. I guess we'll find out. And the null terminating null terminating character, I guess. I think that's what's going on. So we need to add 3. I think that's more like it, but we don't have the lengths yet. So we need str len. Did I have the colon? Yes. So str len 0, colon space, equa instead of db. Really winging it. I don't know what the hell this means. That's right. $ minus hello. I think that means like the position that we're at now, where we're declaring this variable, minus the length of hello. So it goes back to, so it tells us basically how long hello was. Okay. So it's $ minus $ minus str index. I think that's it. Let's try running that. And then, whoops, we need interpreter a new line at the end. There we go. Str 0, str len 0 needs an underscore. Str len 0, str 0, str len 0, references str 0 and str 1, and this is printing those. I think that's kind of right. I'm not sure if this can come after the text section. In Fireship's example, he put it first. Let's see what happens. Let's see what happens. Okay. Seem to compile. Not equal. Printed not equal and then halted. You can see here there is something going on. There's like a tab character here. No, it's a bunch of spaces. And it didn't include the quotes, so that's good. I don't know why there's a whole bunch of spaces there. You know, that doesn't seem right to me. But I'm pretty stoked, you know, that we actually printed something out. So we have all this, except for this label. You know what? Let's do the label now. I think the label would not be too hard to do. So if it was not a known command, but it did end with colon, then we want to add a label, right? Which isn't that just we intended that much. We're gonna have to split it up. I don't like this. Right, no, I don't think we need, the colon is already in the label. So now we go out and we print the label. So we need to do token, just like that. So now if we run that, we have our L1 label here. Cool. So we've done all this. We've done half the program. I think I want to do the jump next. And for the jump to work, we have to have something on the stack. So we can just add a command at the start temporarily. How do we do a push? I just want to do push 5 or something like that. Is it that simple? If I go NASM x86 push. Push and pop and NASM with stack. Push edx push. Quick reference cheat sheet. Push source. If I go push integer. Saying push regs. Yeah, I think he's trying to do it from a register. Let's just try push 5. It's probably not going to work. I feel like you can just do a push with, a hard-coded number. I don't think you have to go to a register. I mean, we might have to move. Might have to do a move. I can't remember how to push onto the stack. So that's probably going to fail. Let's go jump equals 0. Jump if 0. Jump of 0, JZ. But what's it checking? Jump if register is 0. I wish it would say, like, what are you checking? So let's go JZ, maybe we can get some more. Instructions JZ location. Maybe we can go x86 stack location, where stack pointer points. Yeah, I think it's RSP, which is like register for stack pointer. So I think if we want to check, if we want to, what is it? JZ RSP, it should jump if what's on top of the stack is 0. That's with our stack-based language, that's what we wanted. And greater than 0, jump jump GZ, jump quick reference, jump if above. Jump if above. What I'm thinking about is how do we say what it's above? I thought there would be, because we have if not 0, I thought maybe you would have something that says like above 0, but there's only if 0, if not 0. I don't see any other references to 0. So jump if above, I think, is what we want. JA. JA jumps if there's these flags. I don't think I need to worry about the flags. For example, compare these two, then jump. Because the jump needs to... Okay, so we probably got the other one wrong. Let's copy this. Yeah, that's a good point. Like here, we're not even saying where we jump to. So I think we want to still compare like the stack pointer to 0. And then we need our new lines. And then jump to 0 somewhere, and somewhere is going to be, so jump to our label, which is jump greater than 0. We need to have this for our jumps. I think that was the message we had before, and I think to jump to, and then we should be able to go tokens index. Jump 0. So I think that makes sense. We compare two registers or two somethings, and if one is above the other, we go somewhere if EAX is greater than EDX. So if the first one is greater than the second one, in this case, if the stack pointer is greater than 0. Yeah, that's what we want. So I want a JZ example, I think. X86 JZ example. How do we jump if 0? JZ is jump if 0. Comp subtracts its two operands and sets flags accordingly. If the two operands are equal, the subtraction will result in 0. And the flag will be set. So in your example, the jump will be taken if AL was 1, not taken otherwise. Okay. So I think we also want this same compare, which is going to result in a 0, and then we get the JZ. So it's basically exactly the same, except we say JZ instead of JA. I feel like that's it. So here's our, oh, we've got JZ L1 without, we're going to need a space here. JZ space, JA space, like that. So we should push 5 onto the stack, which should mean that 5 is in RSP. Compare RSP to 0, and if that evaluates, because it subtracts one from the other, which means that if RSP is 0 and that's 0, then we should jump to L1 and print out equal. Otherwise, we will print out not equal. That's basically how our program is going to work so far. Okay. Let's see if that works. So it should say, I think we should get string 1 printed because we're going to go to L1. So we should get equal. We're going to go to L1. No, we're not going to go to L1 because 5 is not the same as 0. So we're going to get string 0 printed. We're going to get not. We should get not equal, I feel like. Let's see. Does it compile? Looks like it. Not equal. Wow, I can't believe that actually worked. I can't believe this push 5. Wow, my tea, my poor tea. Can't let it get cold, that's a crime. Ooh, I do like oat milk. I can't believe this push 5 worked. I just thought, yeah, maybe it'll work. And this works. I just thought, maybe if we take the register, I think that's the register that points to the top of the stack. Well, let's confirm. If I go push 0, and then we run this again, I think we should be able to go like this, and then ld out.o dash o out and dot slash out. We get not equal again. Oh, we still have 5. I thought I changed that to 0. If I run that, and then we go like that, not equal. Wait a minute. Because this is the output. I shouldn't run it again. Should just, because I'm compiling again. Okay, so that's still saying not equal, so that's not right. So I did get an error. There's something that I'm not doing right here. If we do that, invalid combination, not equal. Should be jumping to L1 where we get string 1, which is equal. Okay. Something else we're missing out on is we probably should say this is our jump equal to 0. This is our jump greater than 0. Push 0. And let's just make sure that it's not that combination that's wrong. not equal. L1 string 1 equal. Just on a tangent, something I'm curious about with our string constants, which are down here. What if I just do +2? Huh. It still works. What is this number? I don't know. I'm just going to leave it at 3. I think we need to figure that out a bit better. Okay, let's say x86 push example constant, push constant directly, or move push constant directly. Move EAX -11, push EAX, push -11. What you have should be okay, assuming the code is in 32-bit mode. But we're not pushing a pointer. Push word, double word. Push I64. How to push a 64-bit int in NASM. Looks like I've looked at this before. There is no push instruction. As a workaround, you can do one of the following. Go through a register, move it into racks and push racks, go through memory. Let's go through a register. So move racks 0 and push racks. Let's try that. Let's just check that we got what we wanted. Okay. Instruction expected. Out.asm line 4. Move racks 0. Because move doesn't have an E on the end. Nope. Oh. Needed to remove it here. Not equal. Let's try racks. We know we have 0 in racks. Oh. And let's not build this again. Equa. Yeah, there's definitely something going wrong with my string constants. But I think that means we're getting the right thing. So comparing racks is fine. So what about x86 compare top of stack? Compare register with item at top of stack. Huh. Maybe we can't do it straight from the stack. Let's be a bit more specific. He's going to compare RBX. What are the square brackets? What do you think that's about? Is that like address of? I doubt this is going to work, especially when I do that. Operation size not specified. Let's compile that against RSP. So we're moving to racks, we're pushing. What if we just move to racks, compare racks? I keep doing that. I keep rebuilding the assembly. So that's fine. RSP doesn't seem to work. So if we go racks 5, don't run that, then we get not equal. Racks 0, get equal. Ignore the terrible printing, whatever's going on. So our jump worked. So the jump worked. The problem is that we were trying to jump based on what was in the stack, right in the stack. So I think first we need to move whatever's on the stack to racks and then compare racks. Something like that. And we do the same up here. Move what's on the stack to racks, compare racks, and up the top we're doing a push. I wonder if we can just do push 5 still. So we push 5, then we take whatever's on the stack, move it to racks, compare racks to 0, and jump. So we should get equal. Because move. Oh, I think that's the wrong way around. I think that's the wrong way around. Yeah. That's moving from RSP to racks. So we want to do that. Oops. In both places. Run that. Yeah, we get not equal. And then if we were to push 0, son of a bitch. We still get not equal. Do we have to do it like that? You have to push from a register do. Move 0 into racks, push racks. x86 move top of stack into register. That's right, this is where we looked at it. But some of these answers, they're very old and I don't really get it. Mm-hmm. Moving values from the stack to memory. I think we want to move them to memory. We did at one point see that the jump is working. I really do want to get this push working though, because then we can implement our reads, which is similar to this. We need to do a syscall, but it's a read syscall. Then we need to, what we read, we need to push it into the stack. That could be a bit of a tricky one actually. Then we need to sub. I forgot to time, but I can still see the timer. We're nearly at an hour. I think we've got pretty far though. I'm pretty happy that we've managed to get, all of this working. Basically what we need to get working is this. And I would be quite happy just to know that we can push something onto the stack and then use it in a comparison. If we do that, we get equal. So, but RSP is not equal. x86 NASM push onto stack. Am I doing that correctly? Push and pop in NASM with stack. Okay, that's not helpful. How old is this? 2017. He's pushing from a register. He's moving a new value into the register. He's pushing a bunch of stuff from different registers onto the stack. And then he's calling CLion. Interesting. Yeah, I haven't tried to do functions yet. And then he has, okay, has a ret. So he's not, maybe we need to specify Linux. Stat pointer ESP. That was RSP. Push, pop, push the value from the stack into EBX. Yeah. I don't want to do any pops yet. The jump operation doesn't pop. It just looks at the top. Load A from the stack. EBP? Oh yeah, R I think is for, I don't know, 64-bit. Is it like that to say the top of the stack? Whoa. All right, that's the top of the stack. And then I think there's this real fucking weird thing. I saw it in another video. The memory map of the process is that the the heap moves from zero, address 0 up, and the stack moves from the top down. So the stack pointer, the address of the stack pointer is getting lower and lower as you add to the stack. So to go back in the stack, you don't subtract from the pointer, you add to the pointer to go up. So RSP plus 4, I guess, would be like 4 bytes back into the stack. It's really weird. Anyway, we don't need to do any of that because we want the top, so we don't need to do plus something. Okay. So we pushed onto the stack. Yes, truffle, soon. Sorry, we've gone over our hour, but if I run that, we get RSP here, we get equal. Yes, truffle. And then I wanted to change it so that we have 5, run that, we get not equal, perfect. Can I just push a number? Run, not equal, 0, run, equal. Okay, I didn't need that intermediate step. We have it working. We have all of this working. And we have it working so that the jump is looking at the top of the stack, which is how it's intended. Because this language is all stack based. So read will push onto the stack, this will push onto the stack. This will pop those two values off the stack, subtract one from the other, and push the result back onto the stack. Then the jump will act on whatever's at the top of the stack, which is what we have. Kick-ass. I think we should add some more comments to this, like we did with the other things. Add some comments to there and also to there. But I think that's it for now. Okay, I'm pretty happy with that. We have a lot more assembly than we did before. At the beginning, we just had hold. Now we have this data section, which is holding our string constants. We have labels, we have jumps, we have prints, and that's pretty much it. But all in all, I think that's a pretty productive hour.